Hello everyone, this is Dr. Webb. In this abstract algebra video, we're going to be taking a deeper look into fixed fields. So let's start off by recalling what a fixed field is. So given an extension L over K, we're going to take H to be a subgroup of the Galois group of L over K. So H is a subgroup of automorphisms of L that fix all the elements of K. Then from H, we can define the fixed field of H, which will be either sort of fancy script f of H, or sometimes just f sub H, depending on, who's doing it. These are two sort of fairly common notions for fixed fields. The f of H is going to be all the elements of L that are fixed by every element of H, right? So fixed means that it's not moved by any element of H. So all the automorphisms send things in the fixed field back to itself. So one way that this commonly might be denoted is that if we for any element of H, if we restrict sigma to the fixed field of H, so this means that we're only using the fixed field of H as the domain, then sigma is equal to the identity on the fixed field of H. Write it like that. Okay, and so everything in H does not change any of the elements of the fixed field. All of those elements are fixed. So let's recall some preliminary results that we've already seen about fixed fields, either what we've done in homework or talked about in class. So one is that if you have two subgroups of the Galois group, G and H, and G is inside of H, well then you have an inclusion flip when you think about the fixed field. So the fixed field of H is going to be a subfield of the fixed field of G. If K is a subset of L, then K is going to be a subset of the fixed field of the Galois of L over K. Right? And this is just, this one is very straightforward because the elements of K, because in the elements of the Galois group of L over K, they don't move anything in K. So K is not moved by any of those elements, so it is in the fixed field. If H is a subgroup of the Galois group of L over Q for some field L, then H is going to be in a subgroup of the Galois group of L over the fixed field of H. So this is just saying that everything in H is an element that is an automorphism on L that fixes everything in the fixed field of H. Okay, so a couple more results. If K is equal to the fixed field of H for some H that's in the subgroup of the Galois group of L over Q, then K is in fact the fixed field of the Galois group of L over Q. Right? So if K is the fixed field for some subset of the Galois group, then it is in fact the fixed field for its own Galois group of L over K. Right? And so this is what's important to note here is that you don't always have that K is equal to the fixed field for its Galois group, right? So in general, K doesn't have to equal the fixed field for its Galois group. And so this is saying that if, so this result is saying something. And so an example of this, where K doesn't actually equal its fixed field, is if we let L be Q adjoin the cube root of 2 and K to be the rationals, well, the Galois group of this extension is just the identity, and everything's fixed by the identity, and so this means that the fixed field of this is actually Q adjoin the cube root of 2. So that's L and not K. Okay, so K is always going to be inside the fixed field of the Galois group for it, but it doesn't actually always have to equal it. But one case where it does equal it is if it already is a fixed field for some subgroup of the Galois group of L over Q, then it has to be the fixed field for its Galois group. And so that's special. If H is equal to the Galois group for some subfield of L, then H is equal to the Galois group for L over the fixed field of H. Right? So if H is some Galois group for some L and K, then H is going to be the Galois group for L over the fixed field of H. Okay, so the big result for this video is right here, and it says let K be a field over Q and let G be a finite subgroup of the Galois group of K over Q, then the number of elements in G is going to equal the degree of K over the fixed field of G. Okay, and so remember before in the last video when we were talking about the size of the Galois group, we proved that the size of the Galois group is always less than or equal to the degree of its index. And so, so this is what we have right here, that the size of the Galois group of K over the fixed field of G is always going to be less than or equal to the degree of K over the fixed field of G. And G is guaranteed to be inside this Galois group because it fixes everything. It's automorphisms of K that fix everything in G. And so really this is saying that G is then, the order of G then is really as big as it can be. Or in other words, the degree of K over the fixed field of G really is as small as it can be. Okay, so we're going to prove this by contradiction. And so since we know that the Galois group can't be bigger than it, so any subset of it can't be bigger than the degree of the extension. To go by contradiction, the only thing we're going to have to assume is that the order of G is strictly smaller than the degree of K over the fixed field of G. And so we're going to proceed on this, and similar to a proof that we did in the last video, we're going to write out the elements of G. So G is this subgroup of automorphisms, and so we have sigma 1 through sigma n. These are all automorphisms of K. Then we're going to be looking at K over the fixed field of G. So since this is a field extension, we can get a basis. And so its basis elements are going to be alpha 1 through alpha m. And so just by our definition here, the number of elements of G is equal to n. And since the basis for K over f of G has m elements, that's equal to the degree. So the degree of K over f of G is going to equal m. And we have that the degree of G is strictly less than, or we're having the order of G is strictly less than the degree of K over f of G. And so that means here that we're assuming that n is strictly less than m. So let's consider the matrix. We considered this matrix in the last video, so we're going to use it again, except now things are different. In the last time we had that there were less things in the basis than there were elements in the group. Now it's the other way around. right? So now this has m rows and m columns, but the number of rows, this has more rows than columns because m is bigger than n. And so if it has more rows than columns, then the rank has to be less than m, less than the number of rows. Okay? Because at most the rank of this matrix can be n. And so if it has more rows than its rank, there must be a non-trivial linear dependence between the rows over k. And so there has to be some way to get these rows to add them together to cancel them off. And so if we're then looking down, if we're adding the rows together, so think about each row times the C1 times the C2 down to Cm, adding them together, the addition is going to be happening down the columns. And at the end, we have to end up with a 0 row if we added these all together. So breaking these up and looking down each column individually, you'll see down the columns we're fixing the elements of G, right? And so the linear dependence is going to look like through each column, for each sigma j, we're going to have a C1 times sigma j of alpha 1 plus dot 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 C sub m sigma j of alpha m equal to 0. So this is just saying that when you sum down, you do the linear dependence, summing down the columns, then you get zeros for each of them. And so this is happening simultaneously for every element of the Galois group. And we're assuming that each of these coefficients, CIs, are inside our bigger field K. Furthermore, since we have a linear dependence, and there's only a finite number of rows being used, we can just automatically choose the dependence with the least number of CIs not equal to 0, right? So there has to be at least 2 of them that are not equal to 0, or else it's not really a linear dependence. And so it must be, so we can choose the one that has the least of them. Okay, so we have j of these equations. So we have one of these equations for each sigma j in G. Okay. Looking at these, without loss of generality, we can assume that C1 is equal to 1. And if C1 was at the beginning was equal to 0, then we could just relabel our alpha i's such that choosing 1 such that it doesn't have to be, such that it's not equal to 0. And then if it's non-zero and it's not equal to 1, then we can just multiply the whole equation through by C1, by the inverse of C1. And so that will force, if we do that, we can force this entry to be equal to 1, and then the rest of them we can just relabel. Okay. Furthermore, since this is happening for all of the sigma j's in the group, one element of the group is the identity. So there is some sigma j in such that all of the alphas are just sent to themselves. And so, so this is one of the equations here. Now, the alpha 1, alpha 2, alpha m, these are basis for k over f. So what does that mean? Well, these are linearly independent over the fixed field of G because this is our base field. And this is a basis over the base field. And so that means that not all of these coefficients can be in the fixed field of G. If they were all in the fixed field of G, then we would have a linear dependence between basis elements, and that's impossible. So we can be sure that at least some of these CJs are not in the fixed field of G. Okay, so this now is how we have our equation written. And again, this is for all elements of G, all sigma j in G. Now we're going to choose one automorphism, sigma k in G. So here we're choosing sigma k to be in G, and we don't want to pick the identity, so we're picking something else. And we're going to apply the automorphism sigma k to each equation, and then we do sigma k to the whole thing. Well, it's going to distribute through, right? And since it's an automorphism, we can break up what's happening to, we have, say, sigma k applied to C2 sigma j of alpha 2 since this is a homomorphism, we can break up the product and do it each individually. Okay, and so we can think about it like this. And then, since sigma k and sigma j are both elements of the Galois group, if we're combining them, if we're taking the composition of them, then we're just going to get some other element of G. And so we'll just call that sigma L of G. Okay, and so we can relabel this now, combining all of these sigma k, sigma j's into sigma L. Okay, and so we have sigma L of alpha 1 plus sigma k of C2 times sigma L of alpha 2 down to sigma k of Cm times sigma L of alpha m. So what's important here is that this k and L are no longer the same. They're now different. Okay. And so now we have, since this equation here up on top, we originally had some equation for sigma L, we can take this original equation and now subtract off this line. And the important thing to note when we do this is that they both have sigma L of alpha 1 in them. And so if they both have sigma L of alpha 1, and we're taking the top one and subtracting by this second one that's circled, then that's going to cancel off the sigma L of alpha 1 terms. Okay, and so we're going to have one less term in the summand than we had before. Okay, so one less summand than we had before. And the other terms we're going to have, whatever the coefficient was minus sigma k of that coefficient. Okay, so this is what we have. And we can do this for every element of the Galois group. So by applying sigma k to each element of the Galois group, that's just going to reorder all the elements of G. So we're still going to have one of these equations for every element of the Galois group. Now, what this means is, since this is equal to 0, it could either be that each of these coefficients, each of these new coefficients, C2 minus sigma k of C2 through ck, this should be Cm here, Cm of sigma k Cm is giving us another solution, or it could be that each of these coefficients are already equal to 0. Okay, so let's talk about the possibility one. So first of all, this can't be another solution because it's using less coefficients than we had before. And we said that the original one we started off used the minimal number of coefficients. And so if this is using less, then that contradicts that we were using the minimal number to begin with. Okay, and so this is saying that this can't be another solution. And so then we're left with that each of these are equal to 0 for all j. Okay, so if Cj minus sigma k of Cj is equal to 0 for j, that means that sigma k, that means that the Cj's are fixed for sigma k. And if you remember how we picked sigma k, we just picked it to be some element of the group that wasn't the identity. And so then we can repeat this then for any other element of the group that's not equal to the identity. The process is going to work out exactly the same. And so what we'll end up with is that Cj minus sigma L of Cj is equal to 0 for every element in G. And so we kind of skipped the identity, but for the identity, this is trivially true. And so that is included in here too. So if each of these are equal to 0, for every possible one that we choose, then the only possibility is that all of these coefficients are fixed by every element of G. But if every element of G, if all the CJs are fixed by every element of the Galois group, then what must be happening is that the C sub J's were inside the fixed field of G all along, because none of them are moved by any element of the Galois group. And so again, this is true for all J. Okay. But we considered that early on, we said that can't possibly be true, because one of these equations is, one of the original equations corresponds to the identity element, and so then we'd have a linear dependence between the basis elements, alpha 1 through alpha m, and that's impossible because it's a basis. And so that's where we have our final contradiction, and so we can be sure that this can't happen. And that completes the proof. Okay, so again, the theorem we just proved is if K is a field over Q and G is a finite subgroup of the Galois group of K over Q, then the order of G is equal to the degree of K over the fixed field of G. Okay. An immediate corollary to this is that means then that G is actually equal to the Galois group of K over the fixed field of G. Okay. So if G is, so this is using a result that if these orders match up, then it has to be that G is the Galois group. And so this, I think, is a homework problem, and so we're not going to go through it right now, but we will just apply it and use it. Now recall that in the last video, this actually is a special situation to have the order of the Galois group equal to the degree of the extension, right? And we said that if that is true, then this is what we're going to call a Galois extension. So this leads us to final theorem for this video, which will be a much shorter proof than the last one. And it says that if L over K is a finite field extension, then L over K being Galois, so being a Galois extension, is equivalent to K being the fixed field of the Galois group of L over K. Right? And so again, we said that K is guaranteed to be a subfield of the fixed field, but it's special if K actually is the fixed field. Okay, and if that is true, then we have a Galois extension. That Galois extension, again, remember this means that the size of the Galois group of L over K is equal to the degree of the extension. Okay, and so these two properties are equivalent. And in fact, in many books, Galois extension is actually defined as being K is equal to the fixed field of Galois of L over K. And then it has a proof saying that then this is equivalent to the order of the Galois group equaling the degree of the extension. So these two are synonymous with each other. They are equivalent conditions. Okay, so let's prove this. So we're going to go forward direction. So we're going to assume that L over K is Galois. And so that means that the degree of L over K is equal to the Galois group of L over K. But by the last theorem, using the Galois group of L over K, this being our G, well, we prove that the order of G is equal to L over the fixed field of G. And so then this means that the degree of L over K is equal to the degree of L over the fixed field of L over K. And since K is automatically a subfield of the fixed field of the Galois group of L over K, well, so we've got K inside the fixed field of the Galois group of L over K, and this is inside of L. Well, since the degree of this extension is equal to the degree of that extension, that means that we must have equality between these two. And this is a simple fact coming from the Tower law, because we'll have, should be L over K, excuse me. Let's fix that up. So we have L over K is going to equal L over, for the fixed field, I'm just going to shorten it down to F, times F over K. But since these two are equal by the Tower law, that extension must have degree 1, and any degree 1 extension just means that they're equal to each other. Okay, now for the other direction. Well, this actually is even shorter. If K is equal to the fixed field of the Galois group of L over K, then by our previous corollary, or by the previous theorem, we prove that the size of the Galois group is equal to, again, we're thinking about this as being our G, and that being our G. And since these two are the same thing, then it's equal to L over K. So immediately from the previous theorem, we proved the size of the Galois group is equal to the degree of the extension, which means that it is a Galois extension. And that finishes off this proof, which then finishes off this video. So I will see you again soon.